Hello everybody, how are you guys doing? So we just finished probability theory and now we're going to do statistical inference. This is perhaps the most important lecture of the class. So please just listen carefully and try to get the lecture, and especially try to do the problems. Even if you don't get what the lecture is talking about, try to do the problems at the end. This is key. Okay, we'll just continue. Okay, so the first part we'll talk about is population samples and point and interval estimation. Okay, so far we have assumed that we knew underlying probability distributions of random variables and studied properties of summations and transformations of these random variables. However, in the real world, distributions are not generally observed. Okay. In statistical inference, I obtain a sample from a population and use a sample to reach conclusions about the characteristics of a population that I cannot observe. Okay. For example, if I roll a die, okay, I cannot assume that the die is fair. It's reasonable that it's fair, but it's not always true. Okay. In fact, I might actually want to reach conclusions regarding the distribution of the die roll. The underlying distribution of the die roll can be called the population in this case. Okay, it's something, I think it's a fair die. I think it should be 1/6 chance to know the numbers, but I don't know this for a fact. Okay, and so what is the population in this case? Is this the distribution of the die roll that can take on the numbers 1 through 6 and that I don't normally know. Okay, so this is the population. Okay, and then what I want to go more and talk about population now. What is this population and what is it talking about? It can be seen as the total number of objects from which a sample is drawn from, where a sample refers to a few objects drawn from a population. For example, if I want to study the distribution of height, I can select a sample of people from the general population. Is the general population the population I'm referring to when using statistics? So this is the question. Okay, but suppose I'm interested maybe in a trait where the population is only 10 people. Okay, or let's suppose everybody dies, okay, but only 10 people are left on Earth, okay, or something like this. Will statistical inference be necessary if you can sample the whole population? For example, I'm interested to know the average length of an endangered species. So a species that might be only 10 individuals left. And I want to know their length, how long they are. Okay. You can then sample the whole population and calculate the average length. So is statistics necessary if you have the whole population? Okay, everybody died almost, except 10 people are left. I want to know their height, maybe, okay? So I can just get everybody's height. So it depends on your question. Are you trying to know the human population height in general? 10 people is not enough, even though everybody died, right? And just 10 people are left. So you see here the point when I say population, I'm actually talking about this theoretical distribution of human height that I don't know. Okay. So what I'm saying is, right, if only 10 people are left on Earth and I can get a sample from them, Okay, this might not represent the distribution of human height. 10 people are just too little to tell me anything. Okay, so actually the population then is like the distribution of human height, or in this case, the length of some endangered species, theoretical distribution that I don't know. So this is the population. Okay. Okay. Yeah, so we talked about this. So this is the population I'm talking about. And the population is always the distribution of some kind of a measurement or some kind of a variable that I'm interested in. So it's a random variable, the population, okay? Well, now we move to the next one. What about a sample? What is a sample? When I take a sample from a population, I'm taking what are called realizations or draws or observations, you can say, from a population random variable. Okay. In the example of the die roll, the population is the die roll distribution, like we did the previous few lectures. Okay. Then if I roll the die 4 times and I see the numbers 1, 5, 3, 5, or something like this, okay, the sample is going to consist of 4 observations. Okay. So mathematically, call the population random variable x. This is the die roll. The observations are x1, x2, x3, x4. And the sample is called S. Then you can write S like this. In general, a given number of observations is indicated by n. So there is the total sample size is n, I can say, okay? Maybe n is some number, like 100, 50, I don't know, it's just some n, okay? And this is the last number, okay? So as the last observation. So a sample with n observations can be written like this: x1, x2, x3, all the way to xn, like this, okay? And here are some examples of populations and samples. So suppose I have, again, a fair die roll in Monopoly, for example. I roll the die twice, and I observe what the numbers land on, okay? What is the population? The die roll distribution random variable. And what is the sample? Well, I rolled the die twice, so I observed 2 numbers, so the sample is 2. It's 2 observations, okay? What if I flip a coin? I flip the coin once. What is the population? Is the coin flip random variable? Since it is fair, it is 50-50 heads or tails, okay? And this is 1 observation. I flipped it once. If I flip it 5 times and I record heads, tails, each time, the sample will be 5 observations. And then I have some kind of endangered species. Okay, I don't know. You know, I heard in Kazakhstan, actually, you know, Baris. This is the cat, the wild cat that you have here. I heard it's endangered. This is not good. Maybe they're not 10, but maybe there's like 100 in Kazakhstan. You know, this Baris, the wild, you know, it's like a mountain lion or like a white white tigerish, white tiger type of cat, right? And so Well, I'm interested in how long they are. How big are they? But they're endangered. Maybe there's just 10 of them in the wild. This is not going to give me a good representation of how long this cat is, okay? Or how big the cat is. There's only 10 of them, okay? It might be roughly a good idea, but it's not going to be perfect. So actually the population is the species length random variable. The species as a whole. I'm talking about, I have to have trillions of these animals to give me an exact answer of how long they are. I have to have a big number of them. 10 is not enough. If I only have 10, this is just what's left in the wild. This is not the whole population, okay? Okay, so I'm just confirming this again, okay? Then, what am I interested in? Exactly. I'm interested in a couple of things for now. The first one is called point estimation, okay? So back to the die roll, the die question, right, in Monopoly. I'm interested in seeing if a die is fair. Is it fair? That means what? I don't know its distribution. Is its distribution mean really 3.5? Because in theory, if there is a fair die, its distribution mean should be 3.5. Okay? So call the die roll random variable x and its unknown mean, expected value of x, call it mu. This is what I don't know. Okay? Mu is also known as the population mean. This is the mean of a distribution we computed earlier. So again, we assumed that we knew it was fair, and we computed it was 3.5. Right? So, is its mean really 3.5? What am I supposed to do to tell you this? So one way to proceed is obtain a sample of n observations by rolling the die n times, and then taking their average. In particular, define x bar n to be the sample mean of n observations. Okay? To be the sample mean of n observations. Okay? Then x bar n is what you do. You sum all of them up. x1 plus x2 plus x3 to xn like this. Divide by n. It's called the point estimate of the die roll mean mu. Okay? So, suppose I roll the die 3 times and get the numbers 2, 5, 6. I expand the sample and now roll it 6 times total. And I get the numbers 2, 5, 6, 3, 5, 1. Compute the point estimate x bar n for S1 and S2 for these two samples. So the first one I get is 4.3, and the second time I get is 3.7. Notice that different samples give different point estimates of mu, but the actual mu is unknown. Again, it is 3.5 if the die is fair. Assume. Now, is my point estimate? And a point estimate you can kind of think is your best guess. It's your best guess of what the population mean is. Okay. Now, is 4.3 a better point estimate of mu than 3.7? Which one is better? How can you tell? Is it better to have large samples or small samples? Okay. Well, I'll tell you what. Okay. So how to approach the problem? To answer, look at the probabilities of occurrence. I do not know the population mean of the die roll, but when I take a small sample, the small sample could be many possible numbers. And getting a mean of 3.5 might be the most likely outcome, given the die is fair. But I could also get a mean of 2.5 or 4.3. Imagine I rolled just 2 dice and I get 6, 6. Then I assume that the population mean is 6. This is my best guess. If I get a 6, 6, the sample mean will be 6. My point estimate is going to be 6. But this is just one outcome of me rolling the dice twice. I'm taking their average. Okay. So rolling twice or a small number of times will give me a lot of different possibilities for this point estimate, or the sample mean in this case. However, if the sample is very, very large, it will most likely have a sample mean of something closer to the population mean mu. In fact, when a sample goes to infinity, the sample mean is able to pinpoint the population mean with probability of almost 1. It is therefore said that the sample mean converges in probability to the population mean as the sample size goes to infinity. So then, the whole idea, if you think about it rationally, if I roll the die like 1,000 times, I don't expect that the average of these 1,000 will be 4.3, given that the die is fair. Or the average is going to be 5, given that the die is fair. Now, if I just roll the die 2 times, oh yeah, I can get an average of 5. I can get an average of 2. I can even get an average of 1. It's all of these are somewhat likely to happen. But if I roll it 1,000 times and I'm getting an average of 2 or 5, I can say, man, something is wrong with the die, right? This is highly unlikely to occur. Now, it's always likely that even if I roll it 1,000 times, it can always land on 1. Every time it can land on 1, right? But this is like 1 in a trillion chance. It's very, very small, right? Okay. So the whole idea is that when you roll it again a very large number of times, you're really a lot more likely to get something that's very close to the population mean, in this case, mu. Okay. That average will be a lot closer to the population mean. Okay. 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 So this was the point estimate. It's your best guess of the population mean, and you just take, in this case, is the sample mean. You take a whole bunch of observations for population, you compute the sample mean, and it spits out your best guess. Okay. What about the next one? The next one is called a confidence interval. A confidence interval, or an interval estimate, is able to give probabilities that the population mean lies within some range. Okay. As a standard, 95% confidence interval states that there is a 95% confidence or chance that the true population mean is within the given interval. Okay. The confidence interval is symmetrically centered at the point estimate. The larger the sample, the more certain I am that mu is close by, and so the tighter the confidence interval. Okay. Also, the lower the percent confidence I want, the tighter the confidence interval. So this is saying the first step, because I don't know what the population mean is, I gather a sample, I compute the sample mean. Using this sample, the sample, how spread out the sample is, in particular, and the size of the sample, I can compute a confidence interval, a highly likely probability that the population mean is in that interval. This is all it is, okay? So how do you derive this confidence interval? Well, you first have this population you don't know, okay? You gather a sample, okay? And when you gather the sample, the very trick is to treat each observation from the population like a random variable. Thus, each has the exact same distribution as the population. Okay? I treat it like a random variable because I'm interested in the probabilities of the sample mean. I'm interested in the probabilities of the sample mean and how spread out the sample mean is. So, what is this saying? Exactly. This is saying that, again, imagine if I roll a die 2 times and I take the average of the 2 rolls. Okay? Tell me all possibilities that this average could be. Well, I'll tell you, sometimes in a rare chance it can be like 2 or 12. Like 1 or 6. That is, if I get, if I roll twice, if I roll 1, and 6, and twice if I roll 6. But on average, it will be like a pyramid, if you remember from last class, and it'll be very close to about 3.5, 4. These are reasonable like averages. Okay. So tell me the distribution of that sample mean. It's going to be more spread out. You can have low probabilities of getting numbers like 5, 6, even 2, 1. There's still kind of like a reasonable chance of getting those means, right? But again, if I roll it 1,000 times, the die, I would expect, if the die is fair, okay, but I would expect that sample mean to be a lot closer to the population mean. So I would expect the distribution to be very close to the population mean and very tight around the population mean, okay? So if the die is fair, let's say the population mean is 3.5, after rolling it 1,000 times, the sample mean distribution might be between, I don't know, something like 3 and 4. 99% of the time, highly likely it will be between 3 and 4. This is will mean 99% of the distribution is going to be there of the sample mean. Okay. Okay. And then using this fact, it will be very easy to compute the confidence interval. Okay. Okay. So let me now draw it for you. Again, if you didn't understand this part so far, I'm going to draw it just to make things clear. Okay. Okay. Hello, everybody. So now I'm just going to draw out. So basically, what you have is some population random variable x, and it might look something like this. Sorry here. It might look something like this. I don't know. In this case, it's a uniform distribution, okay, or something like this. It's a uniform, and the area has got to be up to 1, right? Here like this, okay. And this is x, and it's like population. And this population, let me just draw it a little better, okay? Okay, so it's going to look something like this. And it's going to have some kind of like a distribution, like this. Maybe it's not uniform completely, okay? But anyway, this x is going to have some mean, and I call this mu. And it's going to have some kind of a spread, or some kind of a variance, okay? And the variance will be, so I say expected value of x is mu, okay, mu, and the variance of x is sigma squared, and the standard deviation of x is sigma. So about the average distance from the mean is sigma, the average distance. This is the standard deviation. All of this stuff, I don't know. I don't know what it is. Then, when I take because I don't know, and I, in particular, for the first one, I'm interested in what the mean is. I don't know what the mean is. And I'm interested in getting a good guess for what this mean is, a good guess. And then I'm interested in a highly probable interval for what this mu can be. And this is the confidence interval, a highly probable interval of what this is. Is it between 5 and 6? Is it between 15 and 20? This mu. Give me a 95% confidence interval, okay? In particular. To do this, I need to know the distribution of my sample, of what I could possibly get in the sample, okay? So what I do is I take a sample. And I call the sample S, like this, okay? And this will be x1, x2 through xn, like this, okay? I take a sample. I treat each one of the observations, each one of them, like a random variable. And this random variable will be exactly the same distribution as x. Exactly the same distribution as x. And the whole idea is that then I will take a sample mean. And it's going to be the sum of all of them, okay, the sum of the I, over n. And this distribution, I'll call this x bar, okay, x bar. And this will be, from last class, if you remember, it will be normally distributed, okay, with the mean of mu and a variance of sigma squared over n. Notice the distribution of x bar is a lot tighter than the distribution of each one of the observations, or the population for this case, okay? The variance of the population is sigma squared. The variance of x bar is sigma squared divided by n, where n is like 5, 10, 20. I don't know how many observations I have, right? So it's going to be a lot tighter, the distribution of x bar, and then the distribution of x. A lot tighter because the variance is tighter. It's going to have the same mean as mu, but a lot tighter of a distribution. Okay? So, plus, I know that the distribution of x bar is going to be normal. I don't know the distribution of the population. Right? You can say this is population. Okay? This is the population. This is the sample mean. And this will have this is a random variable. Now it's a random variable because I'm interested in all probabilities that it could be. So, again, let's draw it a little bit bigger here. I have some kind of a distribution. It's some kind of a population distribution that I don't know what it is, okay? And I'll call this x. Okay, it's going to have a mean. If I take a sample from X and I take the average of the sample, the sample mean, can have probabilities associated with it, with what it could be. What could be the sample mean? And guess what? It's going to be looking like a normal that's going to be very tight around the actual mean. Okay? And this is the distribution of X bar. This is the sample mean, like this. Okay? And its variance and its spread is going to be a lot lower than the spread of the population. Okay? And so, okay, now watch. 95% of the distribution of this X bar will be somewhere here. Okay? And this will be plus minus almost 2 standard deviations away from the mean. If you remember, plus minus 1 standard deviation is 0.68. Plus minus 2 standard deviations, okay, is roughly 96% of the distribution. Okay. Generally, I'm interested in 95% confidence and 95% confidence. Okay. And let's just write here. The standard deviation of X bar is sigma, okay, over watch, square root of n. And the variance of X bar, just remember those, okay, is sigma squared over n, because I take the square root of this to get that. And anyway, because it's sigma over square root of n is 1 standard deviation, and I know that roughly 2 standard deviations away from the mean, okay, is plus minus sigma over this. So this is what I say. It's like this. Minus, it's actually 1.96, almost 2. Yeah, let me just write it here. So this represents, I'll put it here, okay, like this. This is mu minus some standard deviation. So it's going to be 1.96 standard deviations from here, okay. 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 Okay, like this. And this one is going to be mu plus 1.96, almost 2 standard deviations, because almost 2 is, okay, this is sigma over square root of n, like this. And what this is saying, that plus minus this many standard deviations here is going to be exactly 0.95 of the distribution. Okay, 0.95. And these are the cutoff points here. Okay, like this. Okay. Now the sigma from this is the sigma from the population, because the standard deviation of X is equal to sigma. This is from the population. I just use the sample standard deviation for this sigma, and then I can compute how big, and I know n is the sample size, then I can compute how big plus minus from mu, right? Some number minus from mu and some number plus from mu, the mean, the confidence interval is going to be. Okay? Okay, continuing on. I just want to let you know that this is the length of the confidence interval. It's plus minus this, okay, is going to be the length of the confidence interval. And it's very easy to compute, okay? So, just continuing on here. Okay. I talked about this last class, okay? Like this, okay, I talked about this, okay? Okay, now, let's talk about the confidence interval. This is the interval containing mu, or highly probable interval. Watch. So, it turns out that 95% of the x bars are an interval around mu. And I showed you here, 95% of these x bars will be in the interval around the population mean. And the population mean will be the most likely that they are, okay? This is very important. That are an interval, so it turns out that 95% of the x bars that are in the interval around mu will also have mu around them, okay? Within an interval of equal length, okay? And the length is plus minus some number, and this is the number. And this, I think, should be 1.96, not 1.95 like this. If you want to be as precise as possible, it's 1.955. If you want to be as precise as possible, okay. Okay, somewhere between 1.95 and 96. Anyways, like this, okay. Okay, so watch. What is this saying? This is saying that this is the distribution of x bar, just like I drew it, okay? So I want to redraw what's there and what this is saying exactly again, okay? Again, I have some population distribution, okay? And again, this is kind of the population X, okay? This is X. And what this was saying that there's some mean. Let's just redraw it, okay? And make the distribution a little bit, depends on the, how tight the distribution X bar is, depends on the, how tight it is, depends on the sample size. The bigger the sample size, the tighter this distribution is going to be, okay? And anyway, what this was saying, if I have some confidence interval, okay, then notice this is plus minus some number here. I don't know, it could be plus minus 5 from the mean, plus minus 5, okay? This is saying that if I get realizations of x bar, because when I actually get the sample and I observe the sample, I compute x bar, I will get sometimes, it's highly probable, 95% of the time that I will get an x bar here. Here's going to be my x bar, this is 0.95, okay? And so most of the time I'll get x bars, okay? Now I only do the experiment once, I only get one sample. But this is the distributions of all possible samples of that size that I can get, okay? And so most of the time I'll get samples, 95% of the time, in fact, I'll get samples that are very, very close to mu. And once in a while, I might get some samples that are far away from mu. You see how long the interval is here? This is the length of this interval. It turns out that the same interval, let's say around this x bar here, okay, if I have an x bar here, the same length interval is going to contain mu. And if I have an x bar here, okay, like an x bar here somewhere, it's also going to have an interval that's also going to contain mu, the same length one. But if I have an x bar here, or let's say I have an x bar here somewhere, okay, that same length interval, okay, is not going to contain mu. But getting this x bar is kind of rare. It's only 5% of the time I'll get an x bar that's very far away from mu. Most of the x bars that I will get will be very close to mu. Okay, it'll be very close. If I get an x bar far away, it's only 5% of the time. So guess what? 95% of the time, an interval the same length as this is going to contain mu, because 95% of the x bars that are possible are going to contain mu, and only a small number of the x bars are not going to contain mu in an interval. Like this one is not going to contain mu. Okay, and only the x bars that are just outside this interval, they're not going to contain mu in this equal distant interval around them. Okay, and so this is the whole idea behind this confidence interval. I observe some sample. Let's say my sample size is 10. Okay, I get the 10 observations, I compute some x bar. And then I compute this 95% confidence interval. Okay, that's what it's going to be called. It turns out that 95% of the time, the x bar I computed is going to include mu in an equally distant interval, 95% of the time. So highly likely that mu is going to be there for this x bar. Okay, and this is exactly what this is saying here. Okay, okay. And so, like this, okay? Again, this is the equation of the interval here, okay? However, sometimes I might be interested in 80% confidence interval, 70% confidence interval, not necessarily 95%, okay? So, the first step to tell you this interval is to tell you something about some cutoff points. So Z, watch, I'm going to derive it, the confidence interval equation. Start with the standard normal, Z. And Z is between two cutoff points, okay? 1 minus alpha, a probability of the time, okay? And what is Z? Z is x bar minus mu over this. And then I do some math, and I can derive the general form of the confidence interval. Let's call it CI. Okay. Okay. And what is now the logic behind this interval? So recall, for any normal, the probabilities are the same for given standard deviations away from the mean. Suppose plus minus 1 standard deviation represents 0.68 probability. Plus minus 2 standard deviations is 0.955 probability, and plus minus 3 standard deviations is 0.997. The z here, remember before it was 1.96, the z. It represents the cutoff points, but is the number of standard deviations away from x bar n I'm interested in, depending on the significance alpha. So if z alpha over 2 is 3, then I would be 99% certain that mu is within the interval. Here, sigma squared n represents the standard deviation of x bar n. So one standard deviation of this x bar n is sigma squared over n units. Therefore, z times sigma squared over n is the total number of x units away from x bar n that would cover 1 minus alpha probability. So if I'm interested in a 0.997 confidence for mu, then it's going to lie with plus minus 3 standard deviations away from x bar n. Okay. 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 So now, how do I compute this confidence interval? The first place is to start with the z distribution. It's going to look like this. Watch. Okay, I'll show you. Okay. Okay, this is z, and this is a normal 0, 1. Okay. This is 0 like this. And I want to show you what the cutoff points are so you don't get lost. The cutoff points say the following. This is negative z alpha over 2. Okay. This here is z alpha over 2. Okay, like this. And this means this is 1 minus alpha. This probability here, this is probability here. Okay. This probability here is alpha over 2. And this probability here is also alpha over 2. So guess what? If I want my my confidence, high confidence, okay, and what is alpha? I want to define some stuff here. 1 minus alpha is confidence level. Confidence level. And alpha is what's called significance level. Significance level, like this. Okay. So if I want a high confidence level, I want the probability inside to be very high. So it means cutoff points are more spread out. Okay, they're more, for example, if I want this to be 0.8, the confidence, this means the areas alpha over 2, the significance level is going to be, right, here's going to be 0.1 and 0.1 here. Okay, so let's give a numerical example of how to compute these z's. Okay, okay, like this. Okay, let's draw microscope. 1 second here. Let's give just a numerical example of how to compute the z's. Okay. Again, I have the normal. Okay. Okay. And this confidence level is given by the researcher. So sometimes I ask you, give me cutoff points for, okay, 95% confidence. This is the most typical. So 1 minus alpha is equal to 0.95. Alpha equals to 0.05, and alpha over 2 equals to 0.025. And so this is the cutoff point I'm interested in here. Okay, here. It's by symmetry. It's going to be, if I find one of the cutoff points, the other one is going to be the opposite sign. It's going to be the negative. Okay. So here, in this case, I'm interested in here. This is, remember, this is alpha over 2. This is 1 minus alpha. Okay. This is minus z alpha over 2, like this. Okay. So this is equal to 0.95. The area here is equal to 0.025. So it all adds up to 1. And the area here is also 0.025, like this, okay? And then the first step is to get the cutoff points. So this is what I look for. Because in my table, the z table, I have probabilities to the left of some number. So I want the probabilities to the left of a z, okay? Okay, that the area to the left of it is 0.95 plus 0.025. So I want area to left of 0.95 plus 0.025 equals 0.975. This is the area that I want to the left. I kind of already know the answer. This is 1.96, or it should be. But let's double check, okay? Watch. I have the z table, and this is a better one. I'm going to post this, has the negative z's here, unlike the one that's before. So this is a better table than the one in the notes. I'm going to post this on Moodle, okay? And anyway, I search here are probabilities. This is the shaded area, is in the middle. And I'm looking for a shaded area of 0.975. Okay, this will give me the cutoff point z, the right one at least. Okay, and if I know the right one, I know the left one also. Okay, 1 second. Okay, like this. 0.975. Do you see the number? It's exact. And this is 1.96. This is the precision on top. Okay. 1.96 is 0.975. Okay. Okay. So this implies Z, in this case, what is it? Z 0.025. Or the area to the right is 0.025, and the area to the left is 0.975, okay? Is 1.96. This is cutoff point. Or this is, sometimes the book says this is the critical point or the critical value, okay? And for this confidence, this is the cutoff point, okay? Let's do another one. Another one we'll do for 80% confidence, okay? Again, let's just draw the, like this, okay? Okay. For 80% confidence, okay? So how would you do this? Well, that means 1 minus alpha is 0.8. Alpha over 2 is 0.1, okay? And so I'm interested here, the Z alpha over 2. Okay, I'm interested in this cutoff point, and the other one is the same. So the area inside, I want it to be 0.8. And the area on the right here, I want to be 0.1. And 0.1 here as well. And so, what is this? Probability that Z alpha over 2, okay, is less than some number, okay, is less than, probably that's Z, because Z is less than Z alpha over 2. I want this to be what? Okay, 0.8 plus 0.1, so it's going to be 0.9. Okay, 0.9. Because 0.9 is the area to the left of this one, right? The entire one. So I'm just looking to tell me the cutoff point. I'm looking for this guy here, okay? And so I now look at the table, and I look at what now? I look at 0.9, 0.9. And the closest to 0.9 is this one. I just look at the closest one. There's not exact. So this is 1.28. You see, 1.28 is the cutoff point there. Okay. Okay. So Z, in this case, alpha over 2 is what? 0.1. Okay. This is the cutoff point. It's going to be 1.28. So this is equal to 1.28. Like this, okay? Okay. So now we did for 95% confidence, for 80% confidence. You can do for 90% confidence. Try it on your own. Let's do one last example with 90% confidence. And once you know the cutoff points, you're good to go. There's no problems. You don't have to compute them like every time, but it's very easy. Okay. So what about, let's just draw it again, okay? What about 90% confidence? What about this one? Okay. What are the cutoff points? Okay, so you have a couple of cutoff points here. Okay, it's going to be z alpha over 2, and it's going to be the negative of this one, right? Negative z alpha over 2. Let's not forget about that one. And it's going to be 0.9. Because inside, again, 1 minus alpha is 0.9. Alpha is 0.1. And alpha over 2 is 0.05. So the area to the right of this one is 0.05. And here is also 0.05. And the area to the left of this one is 0.95. This 0.95, okay, the shaded. The shaded, okay? And so this is what I'm looking for. Tell me the number here so that the area is 0.95. And this will tell me the cutoff point. So this is what I want to know. This and this. By symmetry, this is the negative of this. Okay? So, again, like this. And let's see now. 0.95. Okay, watch. Okay, it's somewhere in between. It's 1 point. Now, if it's exactly in between, it doesn't matter what you use. This is just a precision thing, right? So it's not that important. It's 1.64, 65, 1.65, 1.64. I use the middle, 1.64. Okay, okay. So this implies z. Well, let's not do z. In this case, what is the area to the right? Is 0.05. Okay, the area to the right of this one. Okay, and this is 1.64. We can say, or 1.65. I just like to add a little 5 at the end here, so it's in the middle somewhere. Okay, so what is this? 1.645. So this is the cutoff point. Okay, and this is the negative one, like this. This. Okay, these are the two cutoff points there. Okay. Okay, so I did this now. Okay, and the example is here. So you can just look at the example, okay? Okay, now let's actually compute the confidence interval. Compute it, okay? So we have everything that we need. How do you compute? If I know the confidence I want, let's say it's 95%, I can, and this is given by the researcher. The confidence level is given by the researcher, okay? The confidence level. 95% means that 95%, there's like a 95% chance that mu is in that interval. 95%. So the bigger the percentage, the wider the confidence interval I need, right, to make sure it includes mu around. So guess what? Let's just look at the formula again. This is the point estimate of mu. This is x bar. This is the sample mean. It's my best guess for mu, right? So the confidence interval, we plus minus some number, the same number, from X bar. Okay, we computed the cutoff point. I know N is a sample size. Now all I need to do is compute S. Okay, and I replace the sample standard deviation instead of sigma. Okay, in case, again, standard deviation population, the sigma is unknown, please calculate from the sample taken using the formula for S. S is known as the sample standard deviation. It can also be a random variable depending on the context. However, in this case, it is an observed value since xi is observed values from the elements. Okay. Okay. So look at question 1. Suppose I roll a die and get the sample of the 6 values. Okay. The sample is like this. What is the point estimate of the population mean? This is the mean of the distribution of the die roll. Yeah, so I get the sample. I don't know the die roll population mean. Again, I want the best guess. So I take the sample that I got, I add it up together, okay, and I get the average. So my X bar, in this case with 6 observations, this is my point estimate. Okay, and this is kind of like my best guess of the population mean. So if I knew nothing about the die, this sample is the only information that I get about the population mean, and my best guess is just to sum them all up and to take the average of the observations. Okay, again. Okay, now let's answer the second question. What is an 80% confidence interval of the population mean? So I want to do it for you guys. By the way, since we're on questions, let's take a little break now and we'll continue. Okay. Hello everybody. So now we'll just continue on. So that was the break. And so let's look at the question. Okay. Okay, I have some values here. Okay. And I'm looking for 80% confidence. Okay, the sample. 624665. 4. Okay, so S. Okay. What is the formula for the confidence interval? This is the first thing you have to write, is the formula. Okay. So the formula looks like this: the probability, okay, that mu is between some numbers. Now, this is what I don't know. I don't know mu. But my best guess for mu is what? Is X bar, or just the sample mean. Okay, the sample mean. And this is my point estimate. Okay, so it's plus minus some number from the sample mean. Okay, and this has to equal to 1 minus alpha, depending on what this probability I want it to be. I want it to be high. I want it to be like 95% probability that mu is between some 2 numbers, right? Or give me this interval. Okay, and then in particular, this is like this. This is the cutoff point. Okay, the number of standard deviations away from the mean. Okay, the number of standard deviations away from the mean is the cutoff point. Okay, okay, alpha times s over square root of n. And s over square root of n is how much each standard deviation is. Each standard deviation is s over square root of n. This is s, not 5. Okay, away from this. And this, on the other side, I have plus. This is minus this number. And on the other side, I have plus this number, the same number. Or it's plus minus that same one. Okay, times, this is times, okay? This is again s over square root of n, like this. And then I just write down what I know. Okay, x bar is what? Z alpha over 2 is what? 1 minus alpha. This is very important. 1 minus alpha. This is the confidence level that I need, right? Is what? S is what? Okay. Okay. And I'll compute S here. So N is what? N. I'll tell you, N is 6. I need to take the square root of N. So 6 is N. Okay. Implies square root of N to square root of 6. Square root of 6 like this, okay? Okay. What is X bar? Well, let's see. What is my confidence level? This here is the confidence level. It should be 0.8. Okay. Do you remember the cutoff point? We just computed the cutoff point. The cutoff point is what? I think it was 1.28. Remember, we just computed the cutoff point for a particular confidence level. For 0.8, it's 1.28, right? We just computed this one. And then what is X bar? This is the average of the 6. 4.833. Okay. And the last thing that we need is this S. So what is the equation for S? I know what it is. Do you remember what it is? It's the sum of xi minus x bar, okay, squared over n minus 1. And what is this equal to? I have how many 6's? I have 3 6's. So instead of writing them down, I'll say 3 times, okay? Because this is 6 minus this is the same thing. 3 times 6 minus 4.833. Okay, squared. Okay. Then plus 2 minus 4.33. 4.83. Just say 4.8 for simplicity, okay? 4.83, like this, squared, plus, watch, I'm showing you, okay? Plus 4 minus 4.83. Squared, okay? Plus, and this is s squared, right? This is, I need to take the square root at the very end. I need to take the square root, so let's not forget about the square root, okay? 5 minus 4.833. Squared divided by, divided by what? 5, because I divide by n minus 1. Okay, so plug into the calculator, show me what you get. Okay, so let's just pause the video real quick and do the computation. Please do the computation on your own in the meantime, okay? So pause the video. Okay, and what is this now? This is, again, this is 2.57. This is what I got, okay? And that implies S, for a standard deviation that we need, is the square root of 2.57. Which equals to what? 1.6, roughly, 1.6, okay? Then, what do? Let's just put it here, what the answer is. So, at the end, what is the confidence interval? Well, you just put in the numbers that you got. So it's 4.83 minus 1.28, okay, times 1.6 divided by the square root of 6, okay, and this is less than mu, and this is like this, and this is 4.83 plus that same thing, right? 1.28 times 1.6 over square root of 6. That equals to 0.8, this probability. Okay. And let's do the math now. Let me erase this a little bit, okay? Like this. I'm just going to erase it real quick, just to create some space. Okay. Okay. And then just compute this number and let's write the answer here. Okay, just compute the. Okay, everybody, we'll just write what the answer is here. Okay. Now. Okay. Okay, so the answer that I got was 3.99, and it's 5.67. This, okay, and this is equal to 0.8. So this is the right answer here, okay? Okay. Okay. This is an 80% confidence interval. So just based on my sample that I got, watch, this is the sample that I got. I think the die is not fair. The die is not fair. And there is an 80% chance that mu, the true population mean of the die, is roughly between 4 and 5.67. It's not, it does not include 3.5 for 80% confidence. If I want, let's say, a 95% confidence, this will be bigger interval. It will be bigger for 95. Because why? The cutoff points will be bigger for 95% confidence, okay? So it might include 3.5. So this is, we'll do this problem in class. In class, we'll do 95% confidence, okay? Okay. So let's end the lecture here.